Hey, this is Acee, and this is the third at-home lab where we have to find the mass of a black hole by using a star that is orbiting the black hole, where we're given the positions of the star, and we have to find the force between the black hole and the star in order to find the mass of the black hole. So what I did was I used the Python program that we made last week at the campus lab. So what this code does is it imports the position data of the star first, and then using that it calculates the change in momentum over change in time, which according to the momentum principle is equal to the net force acting on the star. So then basically after that it uses the so it'll just print that out for me, the FNet, and then also it's going to calculate the position vector between the black hole and the star, and then just the two masses, or sorry, just the mass of the star. So right down here I just have my print statements to find the force and the radius. So after I ran the code, I got a diagram that looked like this, where the black dot is the black hole and this yellow dot is the star. And this is where the initial position was, and then it went around, and then this is where the final was. So the code printed the final position of the star and the black hole, found the distance between them, we were given the mass of the star, and then of course the gravitational constant, and the code also calculated the delta P over delta T of the star, which can be set equal to the gravitational force equation, which is right here. So after I plugged in everything, I got a mass of the black hole that was 7.03 E38 kilograms. So that'll take us to the what does it mean question. So the what does it mean question was, in your analysis you should use the arrows provided in the program to visualize FNet perpendicular, FNet parallel, and FNet. Discuss how these quantities are related to change in momentum over change in time, change in momentum over change in time parallel, and change in momentum over change in time perpendicular. And then discuss how they're different. So they're the same quantities because they're similar because just from the momentum principle, where you can say delta P over delta T is equal to Fnet, and similarly you can break Fnet into Fnet perpendicular plus Fnet parallel, and you can break delta P perpendicular into delta P delta T parallel. So since you can break both these into perpendicular and parallel components, you can set the components equal to each other, like right here. So from that you can infer that Fnet perpendicular correlates to delta P over delta T perpendicular, and Fnet parallel can correlate to delta P delta T parallel. However, they're different because Fnet causes the change in momentum over change in time. If there is, that means delta P over delta T is dependent on Fnet. So if there isn't any net force, there won't be a change in momentum over change in time. So then that takes us to the what if question. The what if question was, imagine the black hole whose mass you found was replaced by a different black hole, but still placed at the same location. Assume the motion of the observed star remains unchanged, is affected only by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found for the original one? And the answer to that question is no, it cannot be different, because if there is no noticeable change in the motion of the star, that means the force would have to be the same. According to the momentum principle, where dp over dt is equal to F net. So if there isn't a change in the motion of the star, that means the gravitational force between the star and the black hole would be the same between the two different black holes in both scenarios. So if the force is the same, then they cannot have different masses, because the force is dependent on the masses. And that's it.